Case Western Reserve University's Institute for the Science of Origins proudly presents the Origins Science Scholars Program. The Institute advances the scientific understanding and application of the origins and evolution of human and natural systems. The Origins Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and MediaVision. It is my pleasure to be not only your host tonight, but the first speaker talking to you about the elusive nature of dark matter. I'd like to talk to you tonight about the elusive nature of dark matter, and I'll start by trying to convince you that we actually need dark matter, and then we'll go on to asking whether it's not just something pretty ordinary that we've missed, and if it isn't, what could it be and how might we find it? Okay. So let's start with the case for dark matter, and it starts over here, not far from where I am, with this guy, Sir Isaac Newton. Well, he wasn't Sir Isaac Newton yet, sitting under some apple tree up at his family home during a plague, and noticing and thinking about apples falling from trees, and looking at the moon and noticing that. Thinking about it as also falling and realizing that there's some connection between those two things, and coming up with his universal law of gravitation, which said that the thing that pulls apples from trees and the things that keeps the moon going around the Earth is the same force, the force of gravity. And we now understand the motion of the moon around the Earth extremely well, and the motion of the planets in the solar system around the sun, but also around each other. They pull on each other as well and perturb that. In terms of his universal law of gravitation, and then in terms of Einstein's revision of that law, the general theory of relativity, which for pretty much everything we're going to talk about tonight gives us the same answers as Newton. And so we get something that we might call the rotation curve of our solar system. And I'm just going to adjust this a little bit. The rotation curve of our solar system, with the sun sitting here at the center of the solar system pretty much, and Mercury going around very fast, Venus more slowly, Earth slower still. And as we get further and further out, the velocity of the planets as they move around the sun is getting slower and slower in a way that's entirely predictable by something we call Kepler's laws of orbital motion, but which are a consequence of Newton's universal law of gravitation. And so this law, Newton's law, applies to all things on scale of the solar system below, as far as we can tell. But when we get to larger scales, we seem to run into a problem. Okay, and the person who first convinced us of that, people had noticed some difficulties before. The person who first convinced us of that is Vera Rubin, who studied the rotation curves not of the solar system, but of galaxies. Galaxies like this one, the spiral galaxy NGC 3949. I wonder if can I make this a little bit bigger? Maybe? Yeah, there we go. Okay, NGC 3949, which looks a lot like our galaxy, the Milky Way. And if a galaxy like this is rotating slowly, we would expect the gravity from all those stars, and there's actually a lot of gas and dust in there to hold the galaxy together. Okay? But if the galaxy was rotating really fast, that would fly apart. Right? Because it would be just like if we sent the Earth moving more quickly. If we gave it a kick, it would escape the sun's gravity. In the same way, the galaxy wouldn't be able to hold itself together. Well, what Vera Rubin did is she looked at a lot of galaxies, and she saw essentially the same thing in all of them, which is that near the center, as you go further out, the velocity of stars is or whatever you're looking at is getting faster and faster, because there's more and more mass between you and the center of the galaxy. But instead of this law turning over and things, as you get farther and farther from the center, getting slower and slower, like we see in the solar system, even though you were outside all of the light of the galaxy, even though if you were beyond, let's say, 15, 20,000 light years from the center, the
rotation curve of the galaxy kept growing and then eventually kind of flattened out. Okay, so these flat rotation curves that Vera Rubin found in many, many galaxies convinced us that there was a problem. These galaxies should be flying apart. And that is, if we took what we saw and asked how much gravity it could provide, it was much, much too little. Okay, so the stars and the gas and the dust are pulling on everything that's lying further away from the center than them, but they don't pull hard enough to explain how the galaxy is keeping together. So Vera Rubin went on and studied many, many, many such galaxies with her colleague Larry Ford, and probably should have won the Nobel Prize for this work, but didn't. But was incredibly influential in the development of modern cosmology. And in fact, a large telescope that's going, a large observational project that's about to start has been named after her. Now, that's not the only evidence that something is wrong with our situation, with gravity on scales larger than the solar system. If we go to scales of clusters of galaxies, we see the same problem, that clusters of galaxies, which consist of many, many galaxies, individual galaxies are also moving too fast to be held together by the individual galaxies. So the matter we see, the stars and gas and dust of the individual galaxies, is insufficient for them to hold each other together using the force of gravity. And so they should be falling apart. And that's what had been seen in the 1930s by this fellow, Franz Zwicky. But he was kind of a unpleasant person, everyone says, and kind of he didn't present as convincing evidence as Vera Rubin. But it turned out to be true. Clusters should also be flying apart. So there's two pieces of evidence that something's amiss with the combination of what we see in our theory of gravity. A more modern piece of evidence that really emerged just over the last, I guess, a little over 20 years, is when we look out at the cosmic microwave background, which is the light from the very early universe. So this is light coming to us from when the universe was much hotter and only about 300 to 400,000 years old. So in that period, there wasn't much around in the universe. There were no stars, there were no galaxies. What there were just sound waves traveling through the hot soup, that we call it a plasma of the early universe. And those sound waves tell us about the contents of the early universe. Okay? So you can think of those sound waves as kind of like the ripples on the surface of this timpani. Okay, and the sound that the timpani makes depends on how tightly you screw down the membrane, the drum head. Okay, so the tighter you screw it down, the higher the sounds. In the same way, the contents of the universe are affected by how much gravity there is pulling things together. And what we find is that there's not enough gravity to be supplied by the ordinary matter, the protons and neutrons and electrons, so the regular matter that we have around us every day and that we can see is out there. Something is missing. We need extra gravity to explain those sounds of the early universe. So we have several pieces of evidence then that something is amiss beyond the scale of the solar system with our application of gravity to those scales. So let me stop there and take a couple of questions.
Luis Fernandez says, could black holes account for the missing matter?
That is an excellent question, and one that I'm going to bring up in a little while. So I'll defer that. But yes, that's a great question. And the answer is maybe.
Stay tuned.
So stay tuned.
Also, can you explain the colors in the chart?
Sure. So those colors aren't real colors. When we look out at the light from the early universe, so if you ever go out on an extremely dark night and look at the sky, this is a picture of the sky that I'm showing you here. You will not see this. Okay? And the reason is that although the light of the when this light was emitted, when the universe was 400,000 approximately years old, the temperature of the universe was about 3,000 degrees Celsius. Okay, so not quite as hot as the surface of the sun, but hot enough that it should have been glowing with visible light. But when you go out in a dark night, you don't see that. And that's because the universe has been expanding. It's expanding now, is expanding then, and it has expanded by about a factor of 1,000 since then. And so all of that nice visible light that was emitted then has been stretched by that factor of about 1,000. And so it's no longer visible to our eyes. We need microwave antennas to detect it. We've been able to do that since the late 1960s. City light in every single direction. Okay, and it's characteristic of something glowing at about 3 degrees above absolute zero, more like 2.7. However, there are very, very slight differences of tens of millionths of a degree, okay, in different directions. And this is a map that I'm showing you of those tens of millionths of degrees differences. Places like these blue places are places where there's it's a little less intense. The red place is a place a little bit more intense. So places of higher and lower intensity, very, very slight. We call those temperature differences. That's kind of you can interpret them as slight differences in the temperature of the material at that point, or slight differences in the density. It's actually a combination of all those things. So what you're seeing here is actually a map of the very small differences in density and temperature of the material of the early universe in different directions. What I've actually done, or what has been done here, is to take the sphere of the sky, so in every direction, and kind of imagine, if you would, that you've taken the sphere and cut it from one side, the North Pole to the South Pole, and then kind of stretched it open to lay it flat on the surface of the screen. Okay, so those colors are just a map, something that we make to make it look understandable.
All right, we have 3 more questions in the Q&A box. So one question just about the map is, are the differences randomly distributed?
That is a great question, and the answer is that they are not just randomly distributed. They are distributed according to some. Our theory tells us how they're distributed. The statistics of them are extremely interesting, and it is in fact the statistics of what goes into that map that is the richest source of information about the early universe that we have.
If there were a planet with the same size as Earth and the same distance from the same size sun in another galaxy, would gravity be the same?
Yes. As far as we can tell, it's a great question. As far as we can tell, Newton's law is universal. He called it the universal law of gravitation, which means it's supposed to apply everywhere the same. So not only is it what we call an inverse square law everywhere, but the constant that determines how strong it is, called Newton's constant of gravitation, is, as far as we can tell, the same everywhere in space and time. Okay, dating back to when this radiation was emitted, when this light was emitted, at least 400,000, when the universe was 400,000 years old. In other words, about 13.5 billion years ago, till now, and everywhere we look, as far as we can tell, it's the same. And we even do experiments on Earth looking at how fast it's changing. If it is changing, we don't detect any changes with time. And of course, Earth is moving through space, so we don't detect any changes with space at the level of a part per billion.
All right. And yes or no, is any of this true in the quantum world?
Well, we live in the quantum world, so apparently it's true. So the question is, the first thing you should ask is, have we just missed something? Maybe there's something in these galaxies that I didn't count. What I said was, everything we see isn't enough. Can we be sure? Okay, so the question is, what is holding a rotating galaxy together? So after all, if you went off to an amusement park and saw some ride like this with the swings spinning around as the central hub turns, you would look and say, well, if I asked you, why don't those swings go flying off, away, out into the amusement park? Well, you tell me, well, it's because there's those steel cables that hold it to the center. And if I spun it faster, those steel cables are still holding it to the center. And they better not spin it too fast so that it doesn't, the steel cables break and the people and the swings go flying off. So something must be supplying that gravity that is holding everything in the spinning galaxies together and stopping those galaxies from flying away. Okay, so there's two solutions, really, two broad classes of solutions to the explanation. Okay, the first one is Newton and Einstein were slightly wrong about the theory of gravity. Well, I guess very wrong about the theory of gravity, because as far as we can tell, 90% of the mass is missing. So we're missing, we only have about 10% of the mass we need to hold those galaxies together. So maybe Newton and Einstein were wrong about gravity. Or there is some missing matter that comprises about 90% of the mass of the galaxy. Now, both of these are worthwhile explanations. For a long time, the only explanation that was taken seriously, I think, is the second one, and it is what I'm going to talk about today. The first one, however, is very interesting, and there's work done on it. It's a bit of a struggle to get it all to work together, to work out. But that's an interesting avenue for research. We have some local experts. Stacy McGaw, chair of astronomy, is one of the leading experts on that theory. I've done some work on it. Other people have done some work on it. But I'm going to focus on that second explanation, that there's missing matter comprising about 90% of the galaxy. And we call that missing matter dark matter. Why do we call it dark matter? Well, the whole point is we don't see it, right? And so it's dark. For whatever reason, when we look at the galaxy, we see the gravity that it's causing, but we don't see the actual stuff causing that gravity. And so our census of the matter of the galaxy is wrong. And so we underestimate how much gravity is being produced. Okay. So perhaps this would be a nice explanation. Somehow this ordinary matter that's masquerading as dark matter that somehow we're missing. Okay, so we should ask ourselves, could we be miscounting the ordinary matter? And by ordinary matter, I mean things made out of out of protons and neutrons, the constituents of you and me and this computer that I'm giving the talk on. So first of all, could there be stars that I didn't count? Well, the thing about stars is they're bright, right? And they shine. And the whole point is I've counted up, when in telling you the story, I've counted up those stars. And so no, stars aren't dark, and so they're not good dark matter. However, stars don't last forever. Our sun's been burning for, somewhere around 4.5 billion years. That means it's been taking its hydrogen inside of it and smashing the hydrogen nuclei together to form through various processes, helium, and eventually the sun will run out of hydrogen to burn. This is a process called fusion that we'd love to harness on Earth, because it's pretty much, it's a nearly inexhaustible source of energy if we could use it. Not completely inexhaustible, because eventually the sun will run out of hydrogen in something like 3.5 to 4 billion years, and then the sun will stop shining. It'll keep glowing because it'll be hot, but it'll start to cool. It'll become something called a white dwarf. It'll eventually shrink down till it's more like, instead of being over 1 million miles across, more like 10,000 miles across, and they'll get cooler and cooler. and it'll get harder and harder to see. Okay, so dead stars are things like white dwarfs and neutron stars, which are even denser. That's something a heavier star would become, or even black holes. But let's leave black holes out of this for now. Let's talk about dead stars in general. So could the dark matter be dead stars? They seem very attractive because they become dark with time. And the answer is, first of all, no. And the reason is because stellar death is messy. The sun doesn't quietly fade away and become a white dwarf. It blows out a lot of its own material in a solar wind, and neutron stars, which are darker and will make better dark matter, even more so. The process of forming a neutron star or white dwarf is inefficient and only leaves behind a fraction of the mass of the original star. Now, remember, I told you that 90% of the mass of the galaxies is in dark matter. And so it's really hard to take an inefficient process of stars dying, becoming white dwarfs or neutron stars, and leaving behind 90% of the mass of the galaxy. Okay, so white dwarfs, neutron stars, and black holes that are made from stars running out of material to burn do not make good dark matter. Well, what about planets? For example, when we look at Jupiter, what we see is the sun reflecting off of Jupiter. So, but what if you took Jupiter, far away from the sun? It would be very dark. Wouldn't it make really good dark matter? And the answer is, if you could do that, well, first of all, Jupiter is not quite dark enough. Actually, Jupiter does glow a little bit on its own because it's shrinking slowly and it's extracting its gravitational energy. And so Jupiter does glow a little bit. The other thing is, as inefficient as it is to make white dwarfs, making planets is extremely inefficient, right? So, and you'll notice, for example, that in our solar system, only about 1/1000th of the mass of the solar system is in planets, almost all of it in Jupiter. So it's very hard to make planets. It's even harder to make planets like the Earth because it's really hard to make stuff like carbon and silicon and iron. That actually happens mostly inside of stars and when the stars blow up. And so that's really, really tough. So no, those things don't make good dark matter. Okay, so when I talked about the galaxy, I said stars and gas and dust. What about the gas and the dust? And again, we can actually look at gas and see it glow, and we can look at dust and see it absorb light. And so we can do a pretty good job at counting all of the gas and dust out there. This is, for example, the Elephant Trunk Nebula, and it's a dark and dense globule of interstellar gas and dust, and we can see the gas and dust. And so we couldn't have missed that much gas and dust. So it's not enough. But there's another problem, and that is that the dark matter has to be in place before the universe is about 100,000 years old, because remember I said that we needed the dark matter to explain the sounds that we see, the acoustic waves in the early universe that we see in the cosmic microwave background radiation. And that is light coming to us when the universe was 100,000 to 400,000 years old. Well, really about 400,000 years old, but we can study the sound waves. We can see how they behaved, over the time slightly before that. And so the dark matter had to be in place then. And stars, there were no stars when the universe was 400,000 years old. Stars appear at the very earliest when the universe is many millions of years old. Okay, so no, that's makes it much more difficult for them to be the dark matter. And in fact, we know that dark matter has to be in place before the universe is about a second old, because that's when the light elements, in particular helium, was made in the early universe out of protons and neutrons crashing together and making something called deuterium, and then crashing together some more and making helium-3 and helium-4. We understand that process very well. We can measure the amount of helium-4 and helium-3 and deuterium in the universe relative to the amount of ordinary hydrogen. And that tells us how fast the universe was expanding back then, when it was about a second old, and how hot it was. And if there was no dark matter back then, the universe would have been expanding at a different rate, and we would have had more helium-4. So no, we need dark matter not just when the universe is 100,000 years old or 400,000 years old, or today. We need to be in place when the universe is about a second old. And it's really hard to make a star get born and die and turn into a white dwarf or black hole when the universe is less than a second old. Okay. So that tells us that stars and dead stars and planets and gas and dust are not very good dark matter. Now, there are some other things we know exist. There are giant black holes at the centers of galaxies. Our galaxy has one. It has one of the smaller giant black holes. It's only a few million times the mass of the sun. Others are 10 billion times the mass of the sun. So we've seen X-ray images of this, and we've seen stars going around these black holes. The thing is, there's only about 1 or 2 per galaxy, and that makes them pretty bad dark matter because they sit in the center of the galaxy. And so that's not how galaxies behave. They seem to have dark matter spread throughout them. Not only that, they take a long time to make a giant black hole. Okay, so that it's really hard to make it. You can't make a giant black hole before the universe is a second old. Another thing that we know exists are particles called neutrinos. They're made in nuclear reactions, like nuclear reactors that generate power, or the one at the center of the sun that powers the sun. And we've seen those neutrinos come out of those nuclear reactors and measured them in detectors. In fact, the fellow who first detected those, Fred Reines, Reines and his colleague Cowan. Reines was chair of the Department of Physics here at Case Western Reserve University in the late 1950s, and won the Nobel Prize for this detection. These would make wonderful dark matter. There's lots and lots of them out there, we believe, that were made in the early universe, except they are extremely light. More than 1,000 times too light. They're so light that although we know they have mass, their mass isn't big enough for us to have detected it yet. So they are so light that means that they don't have enough mass to actually be the dark matter, and they don't fit inside galaxies. It's too hard to bind them into the galaxies. They just would stream out of the galaxies, or they would have streamed out of the galaxies early in the universe and the history of the universe. And so the things we know exist, from stars to gas and dust and white dwarfs and neutron stars and black holes made from stars and giant black holes and neutrinos, all the things that we know exist are not the dark matter.
When did subatomic particles come into being?
Great question. So according to our theory, of course, we don't actually know in the sense of we weren't there. But our theory, called the Standard Model of Particle Physics, combined with our understanding of how the temperature of the universe varies, tells us that long, long ago, the universe was hotter than it is now. Today, it's about 3 degrees. When the universe was about 400,000 years old, it was about 3,000 degrees, a little bit more. Back when it was 1 second old, it was about 10 billion degrees. Okay, so as we go back in time, the universe was hotter. And the hotter, what does it mean to be hot? It means that the contexts of the universe are smashing into each other. Okay, now the faster things smash, if you think about, today we build things called particle accelerators. Okay, particle accelerators are giant machines that smash either protons into protons, or electrons into electrons, or protons into electrons. Why do we do that? We do that because of that equation E equals mc squared that you've probably heard of, that says that energy and mass are interchangeable, right? So if I put a lot of energy in one place, I can produce particles of a particular mass, of a mass equal to that energy. And so early in the history of the universe, particles were running around and hitting each other and making other particles. And so subatomic particles were made back in the early universe when other particles could run into each other and smash into each other and make those particles. It's kind of a chicken and egg thing, that they're all going around making one another, right? And the real question isn't so much when they were made as when they stopped getting made. Okay? So as the universe cools, at some point it cools below the temperature, for example, where I can make a proton. Okay? So that temperature is something like, I think I'll get this right, 10,000 billion degrees. I think I got that right, hopefully. I think that's right. Something like that. We usually use a different unit than degrees. It's a temperature of about 1 GeV, okay, or 1 giga electron volt. Okay? So that's a temperature large enough to make a proton or a neutron. And when the universe gets colder than that, it stops making protons and neutrons. And the question is, why didn't they all go away? Why are there any left? And the answer is that the universe was making protons. It was also making the antiparticles of protons called antiprotons. It was making neutrons, and it was also making antineutrons. And every single antiproton found a proton, okay? And when they got together, they annihilated. Well, not quite every single, but very, very close. However, there were just a few extra protons compared to antiprotons, and just a few extra neutrons compared to antineutrons, and just a few extra electrons a little bit later, when the temperature was only an MeV, a million electron volts, or about 10 billion degrees. Okay, and so we have a little bit those 1 in 10 billion excess of protons and neutrons and electrons got left over. Okay, so the universe early on had lots and lots of particles, and then eventually most of them went away, leaving behind a very small number. And those are the ones that we have left today, unless we make them in our particle accelerators or go to places in the universe where it happens to be extremely hot and particles are smashing into each other.
There's a question, what about WIMPs?
Oh, that's a great question. I will try to answer that in a moment. Having noticed that we need dark matter, and I hope been completely convincing that it isn't just something that we forgot to count, something ordinary. The question is, what could the dark matter be, and how do we find it? And the first candidate, so I'm going to talk about 4 different candidates for what dark matter is. So we don't know what the dark matter is. Of course, we don't actually know that there is dark matter. That other explanation is still out there. But let's say that there is dark matter. Most of us think there's dark matter. What could it be? Okay. Well, the first candidate is something called the WIMP, or standing for weakly interacting massive particle. And for a long, long time, I would say this was the runaway favorite candidate for dark matter. So what is a WIMP? Well, it's a particle, okay, like a proton or neutron. It's massive like a proton or neutron, even maybe more massive, maybe 10 times as massive, maybe 100 times as massive. And it's weakly interacting like a neutrino. So if you notice, I had that in my picture of neutrinos, which I'll run back to. Let's see. Here we go. Here is my picture of neutrinos being made in the center of the sun down here, and flying out of the center of the sun, getting all the way to the Earth. So that means that a neutrino is a particle that can travel through the sun without bouncing around in the center of the sun. It can actually just travel through. A typical neutrino would be able to travel through, a light year of material without hitting anything. Okay? So WIMPs, like neutrinos, are particles that are weakly interacting, so they can travel through enormous amount of material without typically hitting anything. Okay? So now, of course, that's not really an explanation of what a WIMP is. It's just it's describing something. It's a wish list, right, of properties for a particle. However, it happens that particle physicists, without thinking about dark matter, had come up with a theory for completely different reasons called supersymmetry. Supersymmetry is, on one hand, an attempt to explain some of the complications of our theory of particle physics that works so beautifully well, the Standard Model. And on the other hand, it's an implementation of this beautiful symmetry called supersymmetry, a mathematical idea. And what it says is, well, one of the things it says is that for every known particle of the Standard Model, so I'm showing you here 6 yellow things. These are the different quarks that exist in nature, up and down, charm and strange, and top and bottom. And you'll see here the electron and various other, here are some neutrinos. Here's the photon, which is the particle that carries electromagnetism, that also, which is, like the light that you're using to see me. You may recognize here the Higgs boson, which was the last particle of the Standard Model discovered only in 2012. So only just over 10 years ago at CERN. Okay, so this is a beautiful theory, the Standard Model. It works extremely well, but supersymmetry says, well, for every one of those particles, there's actually another particle. Actually, in the case of the Higgs boson, 2 other particles. So just like we have up quarks, there are things called up squarks. Just like we have electrons, there are selectrons. The photon has a partner called the photino, the Higgs boson, the partner called the Higgsino. Okay, and these particles we haven't seen because they're more massive than the known particles of the Standard Model. Okay, and but we can go look for them. And it turns out that 4 of them, I know I've only circled 3, but there are actually 2 different Higgsinos. 4 of them would make really good dark matter candidates because they don't interact easily with ordinary matter. So they're weakly interacting. They're by nature massive because we need them to be massive to explain why we haven't seen them. And so they're particles, which makes them WIMPs. So we go out and we build detectors for these lightest supersymmetric particles. They're called LSPs. Here's a picture of one. It's a giant tank of liquid xenon that is positioned about a mile underground in the Homestake gold mine in South Dakota. And it was actually designed and built largely, with leadership by some members of the physics department here. They've since moved on to work at one of the national labs where the final detectors were built. This is them, several of them standing around in the basement of the Rockefeller building on the Case campus. Okay? And so when a WIMP travels through the Earth and doesn't hit anything, most of the time it will then also travel through the liquid xenon and do nothing. But occasionally it'll happen to hit one of those liquid xenon nuclei and make the liquid xenon glow. And so you can look for that. You can also try to make WIMPs by building a giant accelerator called the Large Hadron Collider, which sits underneath the region around Geneva. You can see the Swiss Alps in the background and Lake Geneva, and even a nice big fountain called the Jet d'Eau here. But mostly you can see this yellow circle, which you couldn't see if you looked from above because it really lives about 100 to 200 or 300 meters underground. And it has protons going around in it extremely close to the speed of light with a lot of energy, and also has protons going around the other way. And it's these places that it says things like CMS and Alice and Atlas. They make those protons going opposite directions smash into each other, and they put these giant detectors. Here is one of those giant detectors with someone standing in the middle. You can see how huge they are. Actually, this is the detector when it's just getting built and it's empty. Here is one of those detectors, a different one when they're about to put it together. Hopefully this person down here moved out of the way before they put the 2 pieces of this together. Absolutely incredible pieces of machinery, really awe-inspiring to go visit. And that's how they found the Higgs boson in these detectors. And so they found the Higgs boson, which was extremely exciting, but they were also hoping to find supersymmetry and lightest supersymmetric particles and dark matter, but so far they haven't. Okay, that doesn't mean they won't. but they haven't. But so the WIMP may still be the dark matter, but it's for many people it is no longer the odds-on favorite. Okay, so we should still keep looking, but we have to explore other possibilities. So another possibility that's been around for a long time, in fact, long enough that I worked on it as a graduate student. My PhD thesis was in part about properties of these particles called axions. These are new, very light particles, and you might ask, well, how can a particle that's very light be the dark matter? I thought dark matter had to be heavy. And the answer is no. Dark matter just has to be hard, not interact very well with light, and has to be very slow moving. And so these axions would have to be produced in a way that makes them extremely, extremely cold. Okay, so much colder than 3 degrees. So these are very light particles moving very slowly. And in fact, they're even lighter than neutrinos, but made in a different way, so they're not moving so fast. Okay, if they're made, we actually don't know if these exist. Well, we know they exist as dishwashing liquid, but that's not what we're interested in. They like the name axion and made some dishwashing liquid that you can get over here in I don't know, maybe I don't know about the UK, certainly in Europe. I've never seen it in the US. That's not the axions we want to find. These axions that we're looking for are a consequence of a possible explanation of why particle collisions can barely tell which way time is running. And that's a whole other story, really fascinating. We're pretty good at telling which way time is running, but particles smashing into each other are much less good. So it needs an explanation why they're not very good. These two people provided it. This is Roberto Pache and Helen Quinn. And they came up with this theory called the Pache-Quinn symmetry, named after them. I don't think they named it after them, but we call it the Pache-Quinn symmetry. And one of the consequences of the existence of that symmetry is that there would be a particle called the axion, which would be running around in the universe. Okay, and it's possible that it would have, very reasonable, that it would have just exactly the right abundance to be the dark matter. Okay, so how do you go about detecting axions? Well, it turns out that axions can turn into photons, particles of light, in the presence of a magnetic field. So people built something called the axion dark matter experiment that looks for dark matter axions turning into photons, and it lives at the University of Washington. And so they've been looking for axions turning into photons. It's a very slow process. You have to tune the detector, or even build a new detector every time you want to check for an axion of a slightly different mass. And we don't know exactly what the mass of the axion is, but they've been making progress over the last 30 years in doing this. Okay. Here's another detector at CERN called the Axion Solar Telescope, and they pointed at the sun and look for axions that would be made in the center of the sun turning into photons. And so far, well, they haven't seen any. Okay. Now, someone asked, what about black holes? And I told you that giant black holes couldn't be the dark matter, but there might have been black holes made very early in the history of the universe, before the universe was a second old, and that would make them good dark matter. It turns out we've looked really hard for these black holes using all sorts of techniques, trying to figure out what they would do to the microwave background, what they would do to white dwarfs and supernova, and et cetera. And there's this very relatively narrow window between about 10 to the 16 grams and about 10 to the 22 grams where black holes could be made in the early universe, could be the dark matter. Okay. The final thing that I want to tell you about is something that I spend a lot of time thinking about, which is chunks of strange nuclear matter. Okay, so these are I would call it an almost ordinary dark matter candidate. They're not quite something that we missed, but it's something that would be made out of particles of the Standard Model. Okay, so you probably would know what a nucleus is. It sits at the center of an atom. An atom is mostly empty space, or it's mostly electrons running around a nucleus, which here's a carbon-12 nucleus, which consists of 6 protons and 6 neutrons. We know, of course, about larger nuclei. Here's a lead-208 nucleus, which has 82 protons and 126 neutrons. If you try to make much larger nuclei, it turns out that anything really larger than lead is unstable. You put those protons and neutrons together, and they just fall apart. And so the question is, what if you put something else in there with them, with the protons and neutrons? And that's called it's called strange nuclear matter, because the thing we put in is strange. Okay, so what does strange mean? Well, remember we talked about up and down quarks, and they make up protons and neutrons. So protons are made of 2 up quarks and a down quark, and neutrons are made of an up and 2 down quarks. You can swap out one of those up quarks or one of those down quarks. Here I've swapped for a strange quark. Strange quarks are a lot like down quarks, except heavier. And so you get this particle, not like a proton and neutron, called the lambda 0, which is unstable. In other words, it falls apart. You might say, well, why would I add something that falls apart to something that falls apart in the hopes of getting into something that doesn't fall apart? Don't worry too much, because neutrons fall apart when they're on their own. And if you take 2 protons and put them together, you'll get something that falls apart, helium-2. But if you add a neutron, which would fall apart on its own, now you get helium-3, which doesn't fall apart. So this is very common in nature, that when you put 2 things together that are unstable, they become stable. And so it may be that if we add lambda zeros, strange baryons they're called, to heavy nuclei, that we get something stable. So strange nuclear matter could be stable. We don't know. We're not even sure we know how to calculate the question. So we really have to go look for it. It would have been made when the universe was only about a millionth of a second old, if it was made at all, or 100,000th of a second old. So we can look for chunks of nuclear matter, strange nuclear matter, that would be wonderful dark matter if they exist. Anywhere between about 50 grams and about 10 to the 22 grams or so, 10 to the 21, 22 grams, or about a millionth the mass of the Earth, would make really good dark matter. They're much rarer than WIMPs. So WIMPs, there would be lots of them passing through you, but a WIMP only has the mass of, kind of the mass of the proton, and these have masses that are, many, many orders of magnitude larger, and so we need many, many orders of magnitude fewer of them. So there's hardly any of them, and so our tools, but each time they hit something, the effects are much bigger. So our likely tools are, instead of very sensitive detectors built underground, like tanks of liquid xenon, they're things like microphones, seismometers, and cameras, used in all sorts of different ways. So let me tell you very quickly about 2 that I'm involved in. The first is that with a couple of colleagues, one of whom you may have heard talk in this series, Ralph Harvey. He's in our Department of Earth, Environmental, and Planetary Sciences. My former graduate student, who's now at the Cleveland Clinic, Jagjit Sidhu, we realized that when these macros, we call them, these chunks of nuclear matter, pass through rock, they melt it. And in particular, if they pass through a slab of granite, they would melt a nice cylindrical path through the granite, and then that cylindrical melted granite would cool and turn into something glassy like obsidian. And that when we looked at it, if we sliced the granite open, we would be able to see this kind of black patch that would be elliptical in the granite, in the surface of the granite. Well, fortunately, people dig up granite and slice it into slabs and polish them and sell them to you to make kitchen counters. And so we can look at those kitchen counters or at the slabs in the warehouses for evidences of dark matter, what we call tenebrites. And we're going to put thousands and thousands of pictures of the surfaces of granite slabs on the internet for citizens like all of us to look at and to find dark matter. And hopefully they will. And that should happen sometime in the next few weeks. In fact, we're hoping to launch on a site called Zooniverse. Here's a second idea of how we could look for these things. And next week's speaker is the first author of this paper. So you'll get to meet him next week, talking about a different way of looking for dark matter. But he and I, together with Jagjit and another colleague of Nathaniel Starkman's, Harrison Winch, realized that these chunks of strange dark matter, as they pass through the atmosphere, could cause lightning. Okay, but the lightning would be extremely straight. straighter than any bolt of lightning that anyone, as far as we can tell, has seen so far. So we hope to launch a campaign to look at the Earth and at Jupiter for extremely straight lightning in the hopes of seeing some and thereby detecting chunks of nuclear matter as dark matter. So I've told you about dark matter. I've told you why we need it. I've tried to convince you that not only do we need it, but it really is something out of the ordinary. It's, none of the things that we just missed. And then I've told you a few of the things that physicists are thinking about: WIMPs and axions and primordial black holes and chunks of nuclear matter, and some of the ways that we hope to find it. Thank you.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.